All right, today we're going to take a look at Unit 8 on acids and bases, Topic 7, where we are looking at pH and pKa. We will be able to determine the relationship between the pH and the pKa of solutions to determine the relative concentrations of a weak acid and its conjugate base. We will also determine how to choose the best indicator for a reaction. Okay, so let's start with pH and pKa. We can use the pKa value, which remember is just the negative log of our Ka, to determine which chemical is in greater concentration, the acid or its conjugate base, at a given pH. So we've seen that there is a key point in an acid-base reaction or a titration, where pH of the solution is equal to the pKa. This is when there are equal moles of acid and its conjugate base. We call this half the equivalence point, or the half equivalence point. So we're going to imagine we have a titration. We've got our weak acid in our container, so HA is our weak acid, and we are adding to it a base to react it. So let's see what happens at different points along the reaction. So right now we're starting with 6 molecules of our weak acid. No base has been added at point A. At point B, we can see we've got 4 molecules of our weak acid and 2 molecules of its conjugate base where the hydrogen has been lost. So those are these two, right? They've lost that little hydrogen atom off of them. And then we've got these other 2 atoms there. Those would be the positive ion from our base. So our base would be like something hydroxide, and so this would be the something part, those 2 spectator ions hanging out. Now at half the equivalence point, that's point C, we can see we've got 3 molecules of our weak acid and 3 molecules of its conjugate base. At that point, we know that the pH is equal to the pKa. Okay, so let's kind of go back to the others. When we had a pH, or when we had more of our acid with that 4:2 ratio, then our pH is going to be less than our pKa. Okay, going to be less than our pKa. Because it's going to be more acidic, right? So we're in that more acidic side, and so our pH is going to be less than that pKa. Now, if we move on past the half equivalence point, we can see we have 2 molecules of the acid and 4 of its conjugate base, along with 4 of those spectator ions. So now that we have more of the conjugate base than we do the acid, we can see right here we got more conjugate base than our HA, the concentration of our acid. Now the pH is going to be greater than the pKa, okay, because we're on that more basic side. And then here we have the equivalence point where the pH is greater than 7 for this one because we're using a strong base. So we've got just conjugate base, so we've got 0 of our acid, we've got 6 of our conjugate base, and then we've got 6 of those ions there. This is where we start to get that salt hydrolysis, and where it reacts with water and kind of reverses things. That's where we get that special reaction happening. So we can see as we start to react the acid, our pH is going to increase. When we're at half the acid, we're going to equal our pKa. When we have, when we've reacted more than half of our acid, we're going to be a pH greater than our pKa until we get to that equivalence point. Right? And because we're doing a strong base with our acid, our equivalence point is being greater than 7. So just to summarize, as we can see, when the pH is less than the pKa, the solution is more acidic. Then we know that the weak acid is in higher concentration. When the pH is greater than the pKa, then the conjugate base, or A-, is in higher concentration. And as we've seen before, when the pH equals a pKa, we reach that half equivalence point, and the concentration of the weak acid and its conjugate base are equal. All right, let's take a look at an example. So the pKa values of two different acids are listed in the table above. We have those shown. Use the information to answer the following questions. So a solution is prepared by combining samples of HC2H3O2, that is acetic acid or vinegar, and NaOH, sodium hydroxide. So we've got a weak acid. We can see there, that's not on our list of strong acids. So weak acid, and sodium is in group 1, so that is a strong base. So weak acid, strong base. The pH of the combined solution is equal to 4. So there's our pH when we pour those two solutions together. They don't give us a molarity or a concentration, but that's what we're going to figure out is where we are in that ratio of chemicals. So which substance, the weak acid or its conjugate base, is present in a higher concentration in the combined solution? Justify your answer. So we can look up here at the table and see that the pKa of the acid is 4.74. We can see that our value of 4 for our pH is less than that. So when it's less than our pKa, we know that that's on the more acidic side. As we go smaller on our pH scale, we're becoming more acidic. So we have to have more acid present. So the concentration of the weak acid, HC2H3O2, is greater since the pH is less than the pKa of the acid. A more acidic solution will lower the pH. So that's how we can analyze a question like this. We've got a second one. A solution is made by combining samples of acetic acid and sodium acetate. A particulate representation of a small portion of the solution is shown below, or on the side. Water molecules and sodium ions are not shown. Is the pH of the solution represented in the diagram less than, greater than, or equal to 4.74? Justify your answer. So we want to count and see what our ratio is of weak acid to conjugate base. So our weak acid is the gray circle with the little one hydrogen atom on it. So we've got 1, 2, 3, 4 of those. And then our conjugate, we have 1, 2, 3, 4, 5, 6, 7, 8 of those. So we have a lot more conjugate base. All right, this is our conjugate base than we do of our weak acid. So that means we're going to be more basic. So what does that mean? Think about it in terms of your pH. Would our pH be greater than or less than or equal to 4.74, our pKa? Hopefully you said greater than because it is more basic. So the pH of the solution would be greater than 4.74 as there is a higher concentration of the conjugate base, therefore increasing the pH above the pKa. All right. So let's continue on this example. We've got the pKa values of two of our chemicals given again. So letter C, a student titrates 50 milliliters of 1 molar ammonium chloride with 1 molar sodium hydroxide. So you can see our chemicals there. A titration curve from the experiment is shown over the side. 3 points on the titration curve are labeled as X, Y, and Z. Use the information from the titration curve to complete the relative concentrations of ammonium and ammonia at the 3 points. Okay, so we can see that we're starting off as being relatively acidic. We're getting a really big increase in our pH to start, and as we move along our titration curve, we do have this like slight incline during our X, Y, and Z points. We can see here that that is our inflection point. That's going to be our equivalence point. And then we end up in the basic side. So that's our NaOH. So we want to see what's going on here. So if this is our equivalence point, that's always good to find. Another good point to find is your half equivalence point. So if our equivalence is 50, then half would be 25. So at point Y, we should have equal concentrations of our acid and its conjugate base. So let's see, at point Y, we would have equal concentrations of NH4 plus and NH3. That would be the logical one there, right? Half the equivalence point, we're going to have equal moles of acid and conjugate base. Half of it has been converted to conjugate base. Okay, well, we can see point X is before that. We can also see that its pH is lower, so we should have a more acidic solution. So we should have a greater concentration of the acid. Remember, acids are the chemical. If you're confused on which one's your acid and which one's your base, remember acids give away hydrogen. Bases take them. So our acid would be the one with the hydrogen, and our conjugate base is what's formed when it loses that hydrogen. So we should have more of the acid form at point X. And point Z would be the opposite. We should have more of the base form because we are above our pKa of 9.26, and therefore we should have more of the base form. All right, so we're just kind of using the titration curves, using the information presented, the pH, the pKa, to determine which chemical is in higher concentration. It's not too bad to be able to compare these. Okay, the last part of this is picking an indicator. This kind of works hand in hand with our pH, pKa. So an indicator is a chemical that changes color within a specific pH range. So we can see some examples down here. We've got methyl red, gives us our pKa, and it says the color of the acid form. They use HIN. IN is for your indicator, H to show the acidic form of it. It's red when it's below a pH of 4. We can see in its conjugate base form, it's yellow above a pH 6. So we're going to go from red to yellow. We're going to, like if we did a titration with this, we'd want that like in between color as our endpoint, that orange color. Bromethymol blue goes from a 6 to an 8. Going from yellow to blue, and phenolphthalein goes from colorless to pink from 8 to 10. This is the one that we actually used for our titration when we did our titration last at the beginning of the semester. We used phenolphthalein. So choosing an indicator is actually quite simple. The pH at the equivalence point, pH at the equivalence point should be close to the pKa of the indicator, as close as you can get. It's not going to be exact, but we want to be close. So which of the indicators is best for the titration of a strong acid and a strong base? Okay, well, we've got some pKa values given here, or excuse me, here. We've got a few more over here. They add in thymol blue, which is different than bromethymol blue. So if we're a strong acid, strong base, we should know by now that our pH is going to equal, oh gosh, this is gorgeous. And our pH is going to equal 7 at the equivalence point. So we want to have a pKa around 7. So we would want to use bromethymol blue for our indicator for that reaction. So our pH equals our pKa. All right, how about this one? The equivalence point of a titration was found to be 8.95. What is the best indicator for the titration? All right, well, 8.95. Is that closer to 7 or is that closer to 9.3? Which one? Should be closer to 9.3, so I'm going to circle it over here. So we would want to use phenolphthalein for this one. Okay, so given a pKa or a pH at the equivalence point, we can determine the pKa of our, or we can pick an indicator based on the pKa of the indicators. We just want them to be as close as possible to each other. We can also determine, given a pKa of an indicator, where the equivalence point might fall, what range it would fall in. So if I'm using phenolphthalein, I know that my change in pH, my equivalence point is going to happen between 8 and 10. Okay, if I'm going to use phenolphthalein. So choosing our indicator is also used, we use that pH and pKa relationship there. So that's all we need to know really about pH and pKa is where does our which chemical is in higher concentration using that information, and how to choose an indicator. All right, that's it. Thanks, guys.